Okay, that's so cute.
Okay, so I first want to thank the organizers for inviting me to give this talk. This workshop really has been a wonderful opportunity for people to get together and really share their knowledge in a very meaningful level. And with that, let me introduce myself. My name is Ji-Woo Park, and I'm a postdoctoral researcher in the group of Yong-il Shin at Seoul National University in Korea. And the submitted title of my talk was Critical Vortex Shedding in a Strongly Interacting Fermi Superfluid. But since the time that I submitted my title, we've actually done quite some more work in the lab. So I updated the title to be Creating Vortex Excitations in a Strongly Interacting. So here's an outline of my talk, and one of the good things about giving this talk later in the week is that people have already given wonderful introductions to the field of quantum gases and strongly interacting fermions. So I'll probably keep things short for the introduction and then jump into the experiments that we have done in our lab regarding the routes to build up turbulence in our superfluid samples. First of which is by using a moving obstacle, so just having an obstacle move through our superfluid sample. And the second method is to thermally quench our atomic samples through the superfluid phase transition, and then relying on the Kibbles-Roth mechanism to generate vortices. Now, in front of this audience, I obviously do not need to emphasize the fact that turbulence is really ubiquitous, practically important, but also quite challenging to study. And one of the many hopes or many motivations of wanting to study quantum turbulence is the fact that in a quantum fluid, the very building blocks of turbulence are very well defined, quantized vortices with a defined unit of circularization. And the simplification, and one of the hopes is that may lead to new insights into the study of classical turbulence, but also notions in classical turbulence can also lead insights into the study of quantum turbulence. But in addition to this relationship, the very fact that we're working with a very quantum fluid, a superfluid, presents us with a unique and very interesting set of questions of its own, many of which arise from the nature that superfluids can flow without friction below a certain critical velocity. So, as we've heard earlier in this week, really the study of quantum turbulence shares its timeline with the study of superfluid helium. And now with the advent of these trapped ultra-cold gases, we are also very interested in studying the behavior of quantum turbulence in our superfluids. And in talks, we've already heard about, for instance, the study of Onsager vortex clustering in 2D quantum turbulence in atomic BECs. Also, Nur has talked about the observation and study of wave turbulence in box potentials. And in our group in Korea, our group is also very much interested in studying the phenomenon of quantum turbulence. And for the most time, we've been working with sodium atomic BECs, but today's talk will rather focus on more recent experiments with our strongly interacting Fermi gases, where I have a little bit more contribution to. So, as we've all heard, what we can do in the lab is we can prepare these ultra-cold lithium atoms in a mixture of two hyperfine states that we can treat as spin up and spin down at very cold temperatures. And the real power that we have is that we're able to tune the strength of interaction between these spin up and spin down fermions using what's called a Feshbach resonance. And so at very low temperatures, we're able to study what's called the BEC-BCS crossover of fermionic superfluidity, where on the one side of the resonance, superfluidity emerges through the condensation of tightly bound bosonic molecules. But on the opposite side of the resonance, it arises through the BCS superfluidity of loosely bound fermion pairs in momentum space. but also at resonance, we have this unitarity limited, very strongly interacting fermionic superfluid, where if I borrow Martin's words, they interact as strongly as quantum mechanics allows them to be. So this ability to tune the interaction so freely has really opened a very exciting direction of research in quantum gases. So we've been very busy studying the nature of fermionic superfluidity in these systems, the creation of topological excitations such as vortices and solitons in these strongly interacting superfluids, but also we can use engineered potentials to kind of trap these atoms in lower dimensions such as 2D and 1D and study the physics of strongly interacting fermions in lower dimensions. And also, by using optical lattices, we're able to put these atoms in an artificial lattice and try to study the physics of Fermi-Hubbard model these days with the optical resolution of a single atom. And in Korea at Seoul National, we also wanted to take part in this excitement. So soon after I joined the team as a postdoctoral researcher, we decided to do a rather large-scale overhaul of our vacuum system and our experimental setup that was already producing sodium atomic Bose-Einstein condensate. So about a third of our vacuum system has been completely rebuilt to accommodate fermionic lithium-6 together with bosonic sodium. And we've put in a new laser system that allows us to kind of touch, tangle, tickle our lithium atoms. And here's a picture of our lab. So here you see there's one optics table that's hosting the vacuum chamber, and inside the vacuum chamber are the atoms, and another optics table producing with the lasers that's producing the light to control these atoms, and these light photons are fiber coupled and then delivered to the inside of the vacuum chamber. Now, I won't go through the very details of how we prepare our strongly interacting fermions, but just emphasize a few key points. And first is that in the process of cooling fermionic lithium, we use bosonic sodium atoms as a sympathetic coolant. And the reason for that is in the process of cooling our fermions, we want to try to preserve our fermion number as much as possible. So in the end, we can have a very large sample of a strongly interacting Fermi superfluid. And the second detail is that after all this cooling process has been done, in the lab, we're able to create a very large Fermi superfluids where typically we have about 10 to the 6 fermion atoms per spin state. So in total, that's about 2 times 10 to the 6 lithium atoms. And the typical condensate fraction that we have is about 85% at unitarity. And one of the key features of our sample is that it's very oblate. So the aspect ratio of our sample in the radial direction versus the tightly confined axial direction of the sample is about 25 to 1. So the very first experiment that we performed with our strongly interacting superfluids is to go and measure the critical velocity to create a vortex dipole in our superfluid sample across the BEC-BCS crossover. And let me motivate a little bit why we wanted to do that. So we all know that a defined property of superfluidity is the ability for the fluid to flow without friction below a certain critical velocity. And above this critical velocity, we know that dissipation sets in the fluid through the creation of elementary excitations, such as phonons and rotons, for instance, in superfluid helium-4. And the framework that we think about the critical velocity is laid out by the Landau criterion, where Christoph has really given a very detailed and wonderful description. And to keep things short, I mean, it's essentially just a restatement of energy conservation and momentum conservation in the context of Galilean invariance. And of course, since the early days of helium research, I'm sure the people in the audience know much better than I do, people have been very interested in trying to measure the critical velocity of superfluid helium-4. And already theoretical predictions were saying that based on the dispersion relation of helium, one would predict a lambda critical velocity on the of about 60 meters per second, which is governed by the creation of photons in the system. And in comparison, people have gone into their labs and tried to measure the critical velocity, and they see that they actually measure something that's much slower than 60 meters per second. And the person who came up with an idea of why there's such a discrepancy is no one other than Feynman himself, who said that the nucleation of quantized vortices can actually lower the critical velocity below the lambda critical velocity. And since then, as far as I know, I believe that the measurement of the vortex shedding critical velocity in superfluid helium has been one of the interesting established research topics in the study of liquid helium, both in helium-4 and helium-3. Now, for atomic Bose-Einstein condensates, obviously one of the first things that we want to measure is the critical velocity of the superfluid. And even before the creation of atomic BECs in the labs, there was this rather well-known theoretical paper, numerical paper by Frisch, Pompeo, and Nika in 1992, where the team has performed numerical simulations of the Gross-Pitaevsky equation to see what happens when a very hard-walled cylinder moves through a uniform Bose-Einstein condensate. And what they saw there was that the critical velocity for vortex shedding in this system is actually determined by the local lambda criterion applied to the atoms, the superfluid that's very close to the surface of the obstacle. And we all know that for a perfect fluid, if you have a cylindrical obstacle that's moving through your fluid, the fastest fluid velocity is achieved tangential to the obstacle, and it has a velocity of twice the velocity of the moving obstacle. So that gives you already a factor of 1/2 relative to your lambda critical velocity. But with considerations of the compressibility of the superfluid, actually the numerical simulations of the Gross-Pitaevsky equations says that for sufficiently large obstacles, the critical velocity for vortex shedding should be about 37% of the speed of sound, which is the lambda critical velocity for Bose-Einstein condensates. Now, in addition to these numerical simulations, there have been analytical approaches to try to calculate the critical velocity for creating a vortex dipole, very much in the spirit of Feynman by considering the energy that one needs to inject into the superfluid and the dispersion of that. And these studies suggest that there should be, for sufficiently large obstacles, cylindrical obstacles, there should be a characteristic 1 / obstacle size dependence in the critical velocity. And so far, experimental explorations with atomic BECs seem to agree better with the notion that it should be governed by the local lambda criterion. And what this story tells us is that despite the importance of vortex excitations and the dissipative mechanism of a superfluid and its transfer properties, the very details of its nucleation process and its relation to the microscopic degrees of freedom are somewhat obscure. And this was one of the many motivations for us to go and try to measure the vortex shedding critical velocity in our strongly interacting Fermi superfluids. Now, as I said, in the vicinity of a Feshbach resonance, the nature of superfluidity actually smoothly changes from bosonic Bose-Einstein condensates to unitary superfluids to fermionic BCS superfluids. And what that means for the lambda criterion is that since the low energy excitations are, the nature of the low-lying excitations change its character from phonons on the BEC side of the resonance to pair-breaking, fermionic pair-breaking excitations on the BCS side of the resonance. The lambda criterion, the lambda critical velocity is actually given by the minimum of the speed of sound and the pair-breaking velocity. So in addition to the ability to tune the speed of sound in our superfluid by changing the interaction strength, there's a second velocity scale that appears on the BCS side of the resonance. And even before performing any experiments in the lab, just sitting in our offices, thinking about what will happen, we were very intrigued because these vortices are really macroscopic collective excitations of the superfluid. So, I mean, on one line of thought, you may think that it should actually follow the speed of sound of the superfluid. And we started to wonder whether if there can be any room or any role of the pair breaking excitations in the nucleation process of these vortex cycles. So with this very motivating question, we went into our labs and started measuring these vortex shedding critical velocities. And the way in which we do that is we prepare our oblate superfluid sample at a given interaction strength that we want to explore. And then once the sample is prepared, we turn on, very slowly turn on a highly focused laser beam that's going to poke a hole through our superfluid sample. And then we move our optical beam, we sweep the position of it by a fixed distance L over a time t with constant velocity. And then we very slowly switch off our optical beam. And then after the sweeping procedure, we release our sample from our trap to perform time-of-flight imaging of our superfluid samples. And if there is a vortex dipole created, they'll appear in our images as these pairs of density depleted holes. And of course, if the velocity was too slow, we won't see anything like this. If it's faster than the critical velocity, we'll see a pair. Or if it's very fast, we'll see pairs of pairs, and so on. And we can kind of perform this measurements as a function of the optical velocity to record the probability to see a vortex dipole in our sample. And once we've measured the probability distribution, we fit a sigmoidal function to our data, and we define the half point as the critical velocity for vortex shedding, given an optical travel distance L in different regimes of the BEC-BCS crossover. So here I show you our data. So the y-axis, these colored data points, are the measured critical velocities for vortex shedding for different optical travel distance, going from very short to long. But still, compared to the size of the superfluid, it's very small travel distance. And as a benchmark, we've also measured the speed of sound in our superfluid sample, and that is shown in these black diamonds here. And the dot dash line is a theoretical calculation of the speed of sound in our sample. And then the dotted line is just the mean field BCS pair breaking velocity. Normalized, all of them are normalized by the Fermi velocity. So this data is very rich with physics. So let me go through some of them that I find more interesting. And the first is that as we reduce the optical travel distance to shorter and shorter distances, we see a general trend of the vortex shedding critical velocity to increase. And that's kind of obvious if you think about the energy of creating these vortex dipoles, because if you assume that you need to provide a certain amount of energy to your superfluid to create a vortex dipole, then as you decrease the distance that you sweep, that means that you need to provide that amount of energy within the shorter travel distance. You need to do it faster. So that's in all regimes. Oh, by the way, the x-axis, in case you haven't noticed, is interaction strength. And in my talk, always the left side will be the BEC side of the resonance, and the right side will be the BCS side of the resonance. And in this plot, unitarity is right here. Okay, so that was the first point, and that's kind of generic. But the really interesting observation is that the rate of increase of our vortex shedding critical velocity is very strongly enhanced in the unitary regime. And this observation is consistent with the general notion that fermionic superfluidity is the most robust in the unitary regime. The third observation is that for the shortest travel distances that we explore in our experiment, we see critical velocities, vortex shedding critical velocities, rather well-defined vortex shedding critical velocities that exceed the speed of sound. And although in this data set it's only shown near the unitary regime, we actually, if we further reduce the optical travel distance, we can also see them on the BEC side of the resonance. And if you think about it, that's kind of surprising, because for a supersonic object, you expect to see shock waves form in the front of your optical beam, and then the vortex shedding pattern should be very irregular behind your optical. But we don't really see a qualitative difference in the response of the critical velocity or the shedding pattern. And we know that if we were to translate our optical beam at this very fast velocity for a longer length, indeed we do see these structures that form. So we think that it has to do with the way we kind of impulsively measure the vortex shedding critical velocity over a finite distance. So seeing this graph, I mean, I was very tempted. I mean, people, I guess, would be very tempted to start and try to compare these velocities to the Landau criterion. But I should warn you, because the Landau criterion is really describing the onset of dissipation through the creation of phonons and pair-breaking excitations, whereas what we really measure in the lab is the response of the superfluid to create a vortex dipole within a finite distance L of the motion of the obstacle. So they're not, maybe it's not comparing apples to apples. So if you're very imaginative, maybe you can imagine that if we were to actually translate our optical beam for an infinite distance, maybe the limit in critical velocity could converge to the Landau criterion, or maybe it could follow the speed of sound. We'll have to see. To better analyze our rich data, we kind of assumed a simple model of dissipation for vortex shedding with our optical beam, where we say that the energy that we provide inject into the rate of energy that we inject into the superfluid from the moving optical beam for vortex shedding is simply proportional to the velocity of the optical beam with respect to the limiting critical velocity that sets the onset of drag force.
Question?
Yes.
So why can't you stir it in a round?
We can, but stirring. So I think in Henning Morris's group, they've studied the critical velocity using an attractive obstacle beam rather than a repulsive with a circular motion. But there you're accelerating. I mean, we also accelerate in the beginning and the end, but they're constantly accelerating, so that presents some challenges. So we assume this model and the energy rate times the time that the obstacle moved that's the time that's needed to create the single vortex dipole. That's just the total energy that we need to inject to create a single vortex dipole. And the time is nothing other than just the distance that the optical beam traveled divided by the critical velocity that we measured. And just reshuffling this relationship, we come to the conclusion that the critical velocity that we measure in the lab should be inversely, should have a linear relationship with the inverse of the optical travel distance. Now, motivated by this relationship, we actually go and plot the inverse of the critical velocity that we measure as a function of 1 over L, where L is the optical travel distance. And on the BEC side of things, we see that our model agrees surprisingly well with the data. However, what's very interesting is that as we move closer to unitarity and past unitarity to the BCS side of things, we see this very peculiar bilinear structure developed in our data. Very intriguing. And the bilinearity, actually, it's strengthened as we go towards the fermionic side of the resonance. And the characteristic obstacle travel distance for those data sets that show this bilinearity, turns out the length scale is roughly set by the obstacle size, which is kind of telling us that about this characteristic obstacle travel distance, there's a rather sudden change in the shedding behavior of these vortex dipoles, which is kind of surprising. And from this observation, we kind of conveniently kind of separate the two regimes of vortex shedding modes and call this the short L mode, or the short L response, because we're plotting 1 over L, and the long L response, or long L branch of vortex shedding. And from the bilinear fits, we're able to extract the characteristic obstacle travel distance where this jump happens. and the slopes of the two branches, and also the limiting critical velocity for the onset of drag, which would just simply be extrapolating the data to the y-intercept of the graph, and then taking the inverse of it, of course. So here I show you these parameters I extracted from our data. So on the top, you're seeing the kind of the characteristic distance where this sudden jump occurs. Middle, you're seeing the slope in the two branches. The long L branch is on the top, short L branch is on the bottom, and the bottom graph is actually showing you the limiting critical velocity that we extract from extrapolation of our data for the two branches, normalized by the speed of sound, theoretical speed of sound. So and the dot dash line is just speed of sound divided by speed of sound, essentially one modulo some scaling factor that we applied to the theory curves to match our data. And then the dotted line is just the BCS period breaking velocity. And let me first bring your attention to the long L branch of the response, in particular to the limiting critical velocity, which are these round blue data points shown here. And surprisingly enough, we see that throughout the BEC-BCS crossover, they tend to rather closely follow the Landau criteria. And what this tells us is that in the long L branch, the onset of drag force that's actually generating these vortices are rather strongly affected by the Landau critical velocity of the superfluid. And in particular, what that means is that on the BCS side of things, it seems like pair breaking excitations are somehow finding a way to play a role in the vortex shedding dynamics. Now, if I switch over to the short L branch, I'm going to bring your attention to the change of the slope as a function of the interaction strength. And in the short L branch, that's just the black gray boxes here. And the response is rather flat as a function of the interaction. And the value of that is actually set at the value that's the same as the BEC side slope. And just looking at this, we're kind of led to think that, oh, maybe the short abrupt sweep branch of the response to the superfluid might be governed by phonon excitations. However, close examination of the limiting critical velocity, where we extrapolate our data, which is shown here, actually it kind of increases from the BEC side as you move on to the unitary regime, and then it stays rather flat to the BCS side. So what that tells us is that, the speed of sound cannot be the end of the story for this branch. There must be something more richer going on with their measurements. So,
excuse me, can I?
Yes.
Where comes the 0.13 factor comes from?
Oh, so this factor we determined by fitting the theory to the data on the BEC side of things. Why it might be there, I think it has to do with the 3D nature of our sample. Our optical beam is probing the center of this, the superfluid sample on the radial plane, but along the tightly confined direction, we're probing the full non-uniformity of the sample. So, probably towards the edges of the superfluid, it's much lower, and that's where it starts.
So you do some density averaging of the speed of sound in this transverse plane?
Yes, we did. Yes.
But it's analytical then.
Yeah. Okay, so we started this experiment with some very clear questions. We've tried to answer them to the best of our capabilities, but in the end, we're still kind of remaining with a lot of questions, despite the fact that they're very interesting, such as how does a pair breaking mechanism actually take part in the vortex shedding dynamics? And one possible scenario that we can think of is, again, as Chris pointed out, we probe the center of the sample in the radial plane, but along the tight axis, we were probing the full inhomogeneity, and maybe towards the edges of the superfluid, pair breaking excitations can kind of locally melt the superfluid, and then that should kind of build on its own, and thereby reducing the critical velocity for creating vortex dipoles. And maybe that kind of process is governing our measurements. But I mean, this is not a definitive answer, it's just a possibility. And in addition to this very pressing question, we're also kind of wondering what determines this characteristic distance other than just a comparison of scales to the experimental scales of what we have in our system. And why is this jump so sudden? And what does it mean? and in reality, what do the two branches represent? And hopefully, with the coming years and more studies, we can try to shed light on these questions. And since I don't want to leave the first half of my talk with a long list of questions, I want to show you something rather fun, which is that we saw while we were playing around with our obstacle beam. And of course, you're not the first to see this. I think Tyler saw this when you were a PhD student with BECs. I called it the Large Vortex Collider. So with that, let me make the transition to the study of the Kibble-Zurich universality and the BEC-BCS crossover with our fermionics. So since Gabriel already gave a wonderful introduction to the physics of the Kibble-Zurich mechanism, I'll be very brief and say that for a system that can undergo a continuous second-order phase transition, if you rapidly punch the temperature of your system through the phase transition, because the characteristic time and length scale of correlations in your system diverge near the critical point, what that means is that the reflex of the system will get slower and slower as you approach the phase transition. And at some point, the reflex of your system is going to be so slow that it can't actually follow the externally imposed temperature quench, which at that point, the system effectively becomes frozen, and the correlations also get frozen with a characteristic length scale psi hat, for instance. And later, when the system's reflexes are recovered in the broken symmetry phase, domains with independent order parameters will form in your system. And as these domains merge at the boundaries, there can be defect formation of objects such as vortices and solitons. And I'm not going to go into too much detail, but just emphasize the key take-home message relevant for my talk, which is that if you apply a linear temperature quench to your system, the defect density that you're going to observe has a very well-defined power law relationship to the quench rate, where the characteristic power law exponent, the Kibble-Zurich exponent as we call it, is determined by the universality class of the system, regardless of the system's microscopic details. And what that says is that the Kibble-Zurich exponent should essentially be kind of determined by the symmetries of your system. And since I only have 4 minutes left, I'll try to rush through things. Of course, because of this universal nature of the Kibble-Zurich mechanism, many experimental platforms have studied the Kibble-Zurich mechanism, including weakly interacting BECs. And what fermionic superfluid brings to the table is that it really presents us with a very unique opportunity to explore the universal aspect of the Kibble-Zurich mechanism. Because with our Feshbach resonances, we have a knob to tune the microscopic nature of superfluidity from bosonic unitarily limited to fermionic. And despite this dramatic change in the microscopics, there should be an overall UN gauge symmetry arising from the superfluid phase transition. Then it's really natural to ask whether the Kibble-Zurich mechanism will change as we tune the interactions or not. And then another very interesting question is at unitarity, as Martin said, it's finding a suitable quasi-particle description of the many-body system when the scattering length has diverged is rather challenging, and you can very much ask the question of whether if the Kibble-Zurich mechanism can actually be applied to such a many-body system. And a similar question has rather recently has been brought to attention in the community of string theorists, where they try to study the Kibble-Zurich mechanism theoretically, numerically, in these holographic superfluids. And because I'm very pressed in time, I'm not going into the details of how we do the quench, but just say that we do a very well-controlled quench. And then we release a sample from the trap and see the images like these, where it's filled with vortices. And we collect these images for different interaction strength as a function of the punch time. And once we've collected these images, we can try to detect and count the vortices and plot the number, the average number of defects of vortices that we see as a function of the punch time for different interactions. So this is BEC side, BCS side, unitary. And a general feature of all of our data sets is that for very short punch times, we see a clear tendency of saturation of the defect number, whereas for rather longer punch times, we see a parallel regime. And to better kind of distinguish the two regimes, we kind of take this empirical model that was actually suggested by you, and we fit this model that captures the behavior saturation together with the power law scaling, and say that, and this transition occurs at a characteristic time t set, and we say that the power law regime are those data points that have punch times exceeding 1.5 times the saturation time of the fits. And then to extract the Kibble-Zurich exponent, we fit a power law function to the power law regime. And here's a summary of the measurements of the Kibble-Zurich exponents in the BEC-BCS crossover. Videos here. Within our experimental resolution, we see that the exponents are rather constant. And if we average the exponents that we measured in different interaction regimes, we see a Kibble-Zurich exponent of 2.24. And to put this number in perspective, we can try to compare this to theoretical predictions on systems in different, for instance, trapping potentials. And for a uniform trap, if you use mean field critical exponents, theory tells us that we should have a Kibble-Zurich exponent of 1/2. If you have strong correlations in your system, you should use RG results, renormalization group results. That tells us that for a uniform system, it should be 2/3. But if you have your sample in a harmonic trap, there's actually a correction factor to the Kibble-Zurich exponent that tells us that it should be 2 for mean field and 7/3 for RG. And this is 2.33333. So our measured average Kibble-Zurich exponent is definitely consistent with the inhomogeneous Kibble-Zurich exponent, a bit closer to the F model predictions. And if the Kibble-Zurich mechanism is really kind of probing the universal aspects of defect formation dynamics in our superfluids, I would say that the behavior of saturation is probing kind of the microscopic details. And the reason for that is the reason why these vortex numbers are saturated at short punch times is because they're destructive collisions, interactions between vortices and anti-vortices in their system. And if you set a simple model of these lossy collisions where you assume that the vortex annihilation is strongly enhanced when the intervortex distance becomes close to or shorter than a characteristic distance that's set by the vortex core size, then the maximal vortex number you can estimate by the radial condensate size squared divided by this length scale squared. And if we were to kind of have a theoretical prediction of what we should see, we can just take the healing length of our superfluid in the BEC-BCS crossover to be the vortex size, the mean field value, and that's what's shown in blue here. And the very good agreement with the data is really telling us that through the physics of saturation, we're actually kind of revealing the physics of vortex core size. So with that, I will conclude and show a picture of the team, and I thank you for your attention.
Thank you very much. So did I understand you correctly? Your vortex number goes down with t to the -1 in time.
Yes.
That was the vortex number, wasn't it? So the mean distance between this, not where you said you have this phenomenological model, or one before, I think.
Oh,
This one, yeah. This one, the straight lines, they are essentially t to the -1, aren't they?
So the question is, are the straight lines t to the -1?
no, that's t to the Kibble-Zurich exponent that we measured.
So what is beta?
Beta is 2 times, and then you get a you get a 1/2 here, so it's actually the Kibble-Zurich exponent within this model. So the beta is actually Actually, the alpha that we extract are the gray circles, and the betas that we extract are the red and orange boxes. And the grid agreement between the two is actually kind of showing us that the way we define the power law regime is done properly.
How do you get to this model? Because you said you back up this model.
Well, maybe I should ask that question to Gabriel, because we're taking it from Gabriel's papers. But it's a very empirical model that just kind of tries to, for very short TQs, NV will eventually become NSAT. But if it's very long, then you win over this time scale so that you recover the power law response.
So we get to this stage, I agree. Yeah, actually, well, my question was related to this as well, which is really nice data, by the way. So you were close to this other model with this F model versus the. But I guess you were comfortable. I mean, because it's within error bars, I guess.
Yeah, I mean, I don't say that we are definitely.
One out.
Yeah, I mean, we were closer.
Yeah.
But I mean, we need to improve on our resolution.
All right. I want to make a comment concerning the vortex shredding.
Mm-hmm.
In our 2011 paper, we relegated to the appendix online. You see something like 50 movies.
Yes.
Where we have all kinds of experiments done. And basically, typical experiments, we put the unitary Fermi gas in a soda can and then stir it around. What we observed there is something somewhat related to what you're doing. Unlike helium, which is incompressible basically, unitary Fermi gas is highly compressible. And we're able to rotate the unitary Fermi gas and maintain its superfluid with creation of vortices at velocities which are much higher than the Landau critical velocity. The reason for that is pretty simple. When you rotate, you form a bulge in front of the stirrer, and the density there increases, and that density leads to Fermi energy increases, which critical velocity increases, so you can maintain that. And basically, we observed similar things. You see that you can rotate. We didn't look at the length, but we looked at the velocity, and we observed you see similar phenomena like we described here. So I want to simply point you to that.
Thank you for your comment.
So I guess the last question, yeah.
Question is about what is the typical lifetime of your vortices, and capability of looking to the vortices right after the phase transition.
Very good question.
What is the lifetime of the vortices, and what's your capability of looking at them right after the phase transition?
So I went through this very fast because I don't have enough time, but of course to kind of determine how much read time we should provide to the sample, we did a rather careful study of the condense fraction and also the average number of vortices as a function of the whole time of the sample. And of course, when I say the saturation is driven by vortex collisions, I mean it's also supported by our observations of the evolution of the vortex as a function of the lifetime, because at very short quench times, with a lot of vortices, we see a very sudden decrease in the vortex number. Whereas for long hold times, it's kind of exponential. So I mean, this is definitely beyond single body decay. And now to address your question of the lifetime of our vortices, of course here, hard to say, but we've seen them for more than a few seconds. But for technical reason, we don't have enough cooling power to pull our Feshbach coils for very long times. So we can't hold our samples for longer than, we don't try to hold our samples for longer than 6-7 seconds. But we've seen vortices live up to that time.
Okay, so I think we can continue our coffee. So thank the speaker. 5 minutes past.
Yes, please.